So, let's get down to business here. Recording has started. So, Chris, you said you had a couple questions related to the lab from Wednesday?
Yeah.
Okay. Anything specific, or are we getting kind of? Did you get through the calculations?
Yeah.
Okay. So the one big thing that we had to do as far as the calculations were concerned was that on this table. Oh, I don't have the right program open. Stand by, everybody.
What happened?
I don't have the drawing program open, so I tried to grab it and put it on there, and Vanessa opened it up. We need some elevator music to sort of fill the time here. We cannot listen to two podcasts on this.
I did not say that. I know, it's not great.
All right.
My bad.
All right. So, the one thing we had to do when we were doing these calculations, there were two columns that we had to talk about. The first one was this column here. Okay? We talked about on Tuesday that, and this actually gave us in today, but one of the terms that we discussed at the beginning of this section was heat. And what did we say that our definition of heat was? Transfer of thermal energy. And we can calculate the amount of heat that is transferred between objects if we know three things. The mass of an object, its specific heat value, and then the change in temperature that occurs. Okay? And then, Chris, I think on Wednesday we talked about here, if you're calculating the heat for water, you need to know the mass of the water, the change in temperature for the water, and then the specific heat value for water, right? And I gave you that specific heat value for water was equal to 4.186 joules over grams degrees C. And we talked about that funny unit for specific heat that just leaves us with joules, and we're done. Okay? Was it 184?
You gave us.
That's I may have given my other classes 186 because I remembered it wrong, but we're talking about like 2,000 something, you know. So. Anyway, so Chris, with those three things, we can calculate the Q for the water, right? The last thing we had to do was it wanted you to calculate the specific heat for the metal. This is the only equation that you guys know of that has specific heat. So we need to rearrange that equation to get specific heat by itself. And when you do that, it looks like this. Okay? All I did was take the right-hand side of this equation, divide it by m, divide it by delta T, and I end up with this. Okay? Is that good? The one thing that we said at that point was the mass of the metal you measured on the front side. The change in temperature of the metal you calculated right here. Okay? But the one assumption we had to make was about the Q value. And what assumption did we make about the Q value? Okay. It's negative, but what is it numerically equal to? Okay. If the water is gaining a certain amount of energy, where did it get that energy from? From the metal. So the amount of energy that the water gained has to be equal to the amount of energy that the metal lost. Just this one's going to be positive, and this one's going to be negative. Okay? What principle are we basing that on? Conservation of energy. Right? With that being said, if we go to the lab, that directly answers the last question on the back side, number 7. Why do we have to introduce conservation of energy before we do this lab? Because what's happening in this lab? What's happening inside the calorimeter? Transfer of energy, but are we gaining or losing any energy? No, it's just moving from one thing to another. So whatever the amount of energy that's gained by one thing has to be picked up by something else to keep the total amount of energy exactly the same. Okay? that good for number 7?
Yeah.
Okay. All right. Okay. Let's talk about number 2. In the case of this lab, there was a lot more water than there was metal. Okay. And if you look at the temperature changes, there's a much greater temperature change in the metal than there was in the water. Okay? If we take it back to this equation, right, the Q is equal to M times C times delta T. Okay? I wrote it this way for a reason. If blue represents water and red represents the metal, what did we say about these two Q values? They're equal, right? So if A equals B and B equals C, what has to be true?
A and C are equal.
A and C have to be equal, right? So if we do this for the water, it has to be equal to this for the metal. Everyone see how I got that?
Yeah.
Good? Okay. For question number 2 specifically, it says, what if there were equal masses of water and metal? If that's the case, what could we do with the M value in this equation? That could cancel out, so we're left with this. Okay? Does the change in temperature for both of those samples have to be the same if the mass is the same?
No.
No. Because there's 2 things over here, right? Change in temperature and specific heat. Change in temperature and specific heat. Do the metal and the water have the same specific heat values? No. We talked about on Tuesday the idea that specific heat tells you how hard or easy it is to heat something up or change its temperature. So in the case of number 2, even though we have the same mass, we won't necessarily see the same change in temperature because what else is different about those substances? Their specific heat values are different. So even though they have the same mass and they trade the same amount of energy, that doesn't necessarily result in the same change in temperature. Okay? Good there for number 2? So for number 3, it says, would this experiment work well if the calorimeter was made out of an aluminum can? Why or why not? Okay. The answer is no. Okay. The big assumption that we make in doing these calculations is that these Q values are exactly the same for the metal and for the water. The amount of energy that is transferred between the metal and the water, the amount of energy the water picks up is the same as the amount of energy that the metal loses. Yes? Okay. That works great inside of this styrofoam cup. Because what does the styrofoam cup not do? It doesn't let the heat from the outside in, but it also doesn't do what, Nick?
It doesn't affect the water's temperature.
It doesn't let the heat from the outside, or from the inside out.
Okay.
Right? But an aluminum can is a good what? It's a good heat conductor. So not only will it let heat from the outside in, it'll also do what? Let heat from the inside out. So if we have the conductor that's actually giving heat off or allowing heat to escape, can we assume that the amount of energy that the water loses is equal to the amount of energy that that the amount of heat that the water gains is equal to the heat that the metal loses?
Yeah.
In the styrofoam cup we can, because what does this prevent? Any kind of heat in or out, right? But is an aluminum can going to prevent that? No. So then we can't make that assumption that the amount of heat gained by the water inside is equal to the amount of heat lost by the metal. Does that make sense? Okay. Better
better insulator? Water or iron? Water would be a better insulator. Why would water be a better insulator? It has a high specific heat value. Miriam, because it has a high specific heat value, what does that mean it does or doesn't do? How about it absorbs heat, but what doesn't happen because of the heat that it absorbs? The temperature doesn't change very much for the heat that it absorbs. It has to absorb a lot of heat to get the temperature to change. Okay? So that means its temperature is much more likely to stay what? The same or consistent. And that makes it a better insulator. Okay? Would the results of this experiment change if more water was used?
Yeah.
No?
Okay.
I feel like it'd be warm.
Yeah, wouldn't it be cold? No, it'd be colder than
Yeah.
water.
So let's go back to this, right? Sam, even though there's more water in the calorimeter, the metal, the red, is still losing energy, and the water, the blue, is still gaining energy. How much energy are they going to trade? The same amount. So now let's go over here, right? So in this part of the equation, okay, we would make the mass bigger here, okay? But if we had more water, how much would it heat up?
Not that much.
Not that much. So this M value would increase, but there would be a resulting change in temperature. Would the change in temperature be as big?
No.
No. So if one of these things goes up and the other thing goes down, the other thing stays exactly the same. Also, we're solving for specific heat. And saying actually that's the case over there, but it also happened over here as well. Okay. But anyway, we're ultimately trying to solve for the specific heat of the metal. Specific heat is a property of that substance. Okay? Specifically, it is an intensive property. Okay? We talked about intensive property like way back in September. Right? But what did we say an intensive property was? It doesn't change with size. It's the same number regardless of how big of a sample it is. So you can just use that as your answer to number 5.
Okay, why does the change in temperature go down?
Okay, Sam, in that case, let's say you have a mug of hot cocoa, okay, and it's too hot for you to drink, so you throw an ice cube in it, okay? Let's say you have a big bowl of soup that's too hot for you to eat, so you throw an ice cube in it, 1 ice cube in each one. Which one's going to cool down more because of that 1 ice cube? The hot chocolate, because there's not as much water that you have to cool down, right? Does that make sense?
Yeah.
So if we increase the amount of water that is gaining energy, it has to spread that energy out more for more water. So the temperature change isn't as big. Does that make sense?
Yeah.
So the change in temperature, which is the average motion of particles, isn't as big because you're spreading it out over more particles.
But if that's in the soup, but if it was in the hot chocolate, it would be a higher change
Because it doesn't have to spread that energy out over as many particles.
Okay.
Good there? And then for number 6, right, would the results change if a larger piece of metal was used? What's the answer probably going to be there? No, because once again, what do we know about specific heat? It's an intensive property. It shouldn't matter on the sample size. And we could go through those arrows again on the red side, and we'd see the same thing. Miriam, go ahead. Oh, you're just... Just to help. Yeah, okay. Any other questions regarding lab? Which one is it closest to?
Oh.
You were actually measuring it. Now you want to compare it to some known values. All right. As far as lab goes, why don't we take a break? Whatever. Yes.
Is it
No, that's actually good.
Okay.
Because in the case of the specific heat, right, you were doing the same experiment 3 times, right? You're solving, and you were trying to solve for the specific heat each time. It was the same kind of metal, so should you get the same answer each time? Yeah, you should. Okay. Well, if you got the same answer each time, or close to it, then yeah. Isn't it good? Isn't it good when you're like, we actually did it right? Actually, that probably should happen more often. But you know, I'm not saying. I'm saying.
Say something that's all the same, like when you're on a test, you see like all A's.
Right.
Or something you're always like, I.
So in this case, though, we're doing those multiple trials to make sure we're getting the same number. All right. Let's shift gears, and let's start in on the last section relating to this unit on heat energy. So let's first cover some of the topics we talked about before. Okay. So thermal energy is what this week has been about. What does thermal energy deal with? What are we concerned with when we talk about thermal energy? Movements? No, movement and position is more of a mechanical energy. When we talk about thermal energy, we're talking about what? Movement of the particles. And Miriam, when we talk about the particles, what particles are we talking about specifically? Molecules or atoms, depending on if we're talking about an element or a compound. Okay. All right. One of the terms that we introduced back on Monday was heat. And we just talked about heat. Heat is the transfer of thermal energy from one object to another. Okay? The beginning of your outline recovers heat, right? So, heat is the transfer of thermal energy, right? From one object to another because of what? What has to be the case if we're going to have transfer of thermal energy? Well, temperature difference. Transfer of thermal energy from one object to another because of a temperature difference. And then more specifically, how does heat flow because of that temperature difference? High temps to low temps, right? So heat will flow spontaneously from objects with high temps to objects with low temps. Yeah.
Is there any case of like 2 objects at the same temperature, just one getting hotter and one getting cooler?
No, not naturally. Yeah, because part of we talked about that idea that with the were you on Monday when we did the pool balls that are running into each other?
Yeah.
Okay. That would be like, 2 objects that are sort of moving the same speed and they run into each other and one gets slower and one gets faster. That just doesn't happen. They would just bounce off each other and they basically be going the same speed they were before. Okay. All right, we're good with heat? You're good.
Okay. Well, two bodies are like dead. Do they move at all?
Move in what way?
Move at all. Like, say they're like gonna fall off like a bed.
Right.
Like, would they fall off the bed?
Sure, because gravity's still acting on them, right?
Yeah. Okay. So they would.
Yeah, it is. I mean, they would.
Whoa.
If you're talking about a dead body, now it's pretty much just like it's just this, right? I mean, it's like any other object. So if it's sitting on the bed, there's a gravitational force acting on it, but there's a force from the bed that's acting on it, and they balance each other out, and it doesn't move.
But it's like on the edge.
Okay,
It would
that would.
fall off.
That would be like, same thing like this. How close could I put it to the edge without getting, it fall off, that kind of thing. If it's here, right? If it's here, even though part of it's leaning over the edge, will it fall eventually?
No.
Not unless what?
And no.
Not unless another force moves it and makes it move a little closer to the edge. That kind of thing.
Don't like dead bodies still like move until their muscles spasm.
There could be that. There's.
No, it's so weird.
No, like they decompose, don't they? It's like they start to shrink and
That could be too.
then there's like a little mini person. They get big.
All right. Let's talk about. Sorry. So, we just went over again what heat was, heat being that transfer of energy. Now let's talk about how we accomplish that transfer of energy. So the first way that we talk about a transfer of energy is by conduction. What's the requirement for something if we're going to transfer heat by conduction? There's one word that we're looking for when we discuss conduction. That's going to happen any one of these two. Yes, but there has to be something in particular that has to happen. Well, that's what any transfer of energy is heat. This is one way that we do it, Parker. They have to be touching. It has to be contact. Okay? So, by definition, conduction is the transfer of thermal energy with no transfer of matter. But Parker, like you said, if we're going to do that, okay, there has to be contact between those particles. Okay? Allison, go ahead.
What does that mean with no transfer matter? Like they don't more shape or whatever?
So, the energy flows from one place to another, but nothing actually takes it there. Okay? The one example being this, right, Allison? Let's say you really, really, really have to communicate with Pierce. Okay? You have the ability to whatever, okay? That note that you need to send to Pierce, that's the energy. It's the ability to cause change, okay? Can you get that note to Pierce without actually taking it to him? Yeah, how do you do it? You give it to Chris, Chris gives it to Wolf, Wolf gives it around, blah, 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 right? We go that way, okay? You could throw it, okay? That's something different, yeah, that's something a little different, but...
Radiation.
Yes, that's radiation. So, Allison, in that case, we have transferred energy without actually transferring matter. You haven't taken that note from there to here, but it's got here. But the only way that that happens is if what? Well, yeah, somebody else gets it, right? So that requires that you have the ability to pass the note from there to there, from there to there. No. What if I spread your desks out real far? Now can you get that note from you to Pierce by passing it from one person to the next? Too far to stretch. Okay, then no, which means that this form of energy transfer, right? Now, there's other ways to get the note to Pierce, but this form of energy transfer depends on what? It depends on contact. You have to be able to get the note to Chris. Chris has to be able to get the note to Wolf. Wolf has to be able to get it to Neuraj. Does that make sense? Okay? So, now, like I said, there are other ways we can do it. But using this way, that has to be the case. Okay? So, if we talk about states of matter, what states of matter are generally going to be the best conductors? Solids are really good conductors. Wait, I should have amended that statement. Things that are conductors, solids, that object in a solid form is a good conductor. Okay? Conduction in gases is generally slower than solids and liquids. Why? Particles are really close together in a solid and a liquid, but pretty spread apart in a gas. Okay? Allison, if you guys were spread apart really far, right, could you walk over to Chris, give him the note, then Chris walk over to Wolf and give him the note? That's still conduction, okay? It's just going to be slower than if you just go boom, 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 okay? This looks better on different projectors. This one's a different projector.
White and yellow at the top.
When it's
That's like one of the things.
I know. It really should be black. It really should be black. Actually, it really should. Easy. Hold on. Hold on. Settle. Is that better?
Yes.
All right. Now, just to clarify a point, okay? Not all all solids are good conductors. Okay? If we go back to our note passing example, right? In all likelihood, okay, if we try to pass the note this way, if I had to guess, where's the note going to stop? It's going to stop at Niraj, right? Why, Niraj? What are you trying to do during class? You're trying to pay attention and learn stuff, right? You're not into passing notes. Okay? So, in that case, Niraj is not a good conductor, not because he's not a solid. It's still a solid, but it's more the property of that material. Okay? Ice isn't a good conductor, not because it's a solid. It is a solid, but it's made up of water. And water isn't a good conductor because of what it's made out of. Does that make sense? So conduction in gases is generally so solids are the fastest conductors if we talk about something that's a conductor, right? So if we talk about like a copper rod, okay? Copper is a good conductor as a solid. It's a better conductor as a solid than it is as a liquid or a gas, okay? Turning copper into a liquid and turning it into a gas is obviously hard to begin with. But if we had some liquid copper and solid copper, it would be a better conductor as a solid than it is as a liquid. However, liquid copper, I don't know this for sure, but liquid copper might be a better conductor than this table is as a solid. Not because of their state of matter, but because of what they're made out of. Does that make sense? So not all solids are good conductors. Let's make sure we make that point clear. Okay. You there? Good.
What if a solid has like a lot of air pockets?
Okay. That actually gets us into the next part. Good transition. Yeah. So let's talk about thermal conductors. So definition, right? Definition of a conductor. Actually, Anthony, let's go here. Let's do this first. Hold on. So let's talk about an insulator. No, like this. Okay. So, what's an insulator? Okay, sorry, my bad. On your outline, it actually says thermal conductor twice. Roman numeral 3 and Roman numeral 4 both say thermal conductor. Change Roman numeral 4 to thermal insulator, if you would please. I know.
First with the yellow,
I know.
white, and then this.
So you know what happens? You know what this is? Usually, like, what time of year do I get to this section? You know, it's like you know, it's almost May. It's like, you know, like. So basically, I'm telling you that I get lazy, but you're not allowed to. That's not true because look what just happened, right? I just changed my PowerPoint, so future generations didn't have to go through what you've gone through. All right. Your pain has caused their gain. There you go.
No pain, no gain.
All right. Material that conducts energy poorly. Okay.
How does it say well?
Let's say well. Probably because I just copied and pasted it. Where? No.
Oh,
So, all right. So let's go insulator first.
Ah.
Okay.
Well,
Ah.
you could set that first.
Sorry. Apparently not everybody got that message. Apologize. Okay. So Anthony, because you asked that question, I wanted to go here first. Okay. So let's go Roman numeral 4. Right. A material that conducts thermal energy poorly. Okay. Wooden or plastic handle on a pan. Are those solids, a wooden handle or a plastic handle? Yes. They conduct energy poorly because they are bad conductors. Okay? That's like Niraj not passing the note to the next person. Okay? However, let's talk about plastic foam, or like let's talk about a styrofoam cup or a wool sweater. Okay? So, a big sweater, a big poofy sweater, keeps you warm when it's cold outside. Okay? And scratchy. But, okay, or think about your big poofy coat in the wintertime, right? What does that coat have a lot of in it? Air pockets. this styrofoam has a lot of air that's mixed into the styrofoam. That's why it's so light, right? It has a low density. What have we said about gases in general? What kind of conductors are they? They're poor conductors. So even if the sweater or whatever, not that a sweater is made out of a good conductor, right? But even something that's made out of a conductor, if it has a bunch of air pockets in it, will it conduct things easily? No. Allison, that's like your guys' desks all spread out, right? It's hard to get the message through. It's hard to get the energy through, not because we're not willing to do it, but because there's just so much space there, right? In the wintertime, you wear your big poofy coats, right? What do you wear underneath your big poofy coats? A sweater and then maybe a long sleeve shirt underneath that, right? By dressing in layers, what are you doing each time you put a new layer on? You're trapping another layer of what? Another layer of air goes between you and your shirt. And then another layer of air goes between your shirt and your sweater. Layer up, because now not only do you have more of the poofy clothes, but you also have another layer of air in there. Okay? Anthony, go ahead.
Like, is there anything that can, like, trap the energy?
Well, anything is kind of the key there, right? If there's going to be no transfer of energy, what does there have to be between point A and point B? Nothing. Okay? If you have a really good thermos, okay, like a really good, like a camping thermos or something like that, okay, that keeps, or like something that you take like to like a outside like football game or something like that, that can keep your hot chocolate warm for like hours, okay, or cold water cold for hours, okay. It actually has a little vacuum layer. It's got an inside wall and an outside wall, and in between those two walls is a little vacuum layer. Because what's in between the vacuum layer? Nothing. So in between the inside wall and the outside wall, it doesn't conduct energy. Does that make sense? Not air. A really good thermos actually has a vacuum. So if you break it, it actually makes a popping sound because it's like there's nothing there. Now, a regular thermos, like one you used to get like in your lunchbox when you were like in elementary school, like that thermos has air in between two layers. Like so it has like an inside part where you put your drink, and there's like an outside part. Air is a pretty good insulator, but it's not as good of an insulator as nothing. Does that make sense? Okay. So a really good thermos has a vacuum layer. Okay.
Yeah, what about like an Under Armour?
Right.
It's really tight, so.
Right. In that case there, what we're doing, so first, like winter Under Armour and summer, like cold gear and heat gear, they're two different materials. They're made different ways because they're trying to accomplish different things. But an Under Armour, what's in there probably, like, see, I don't know exactly how it works, but there might be something about the material that it's made. It's getting rid of the water, which is good because water actually makes you a little colder because it has a high specific heat value. So that's one of the things. It's keeping you drier. If you wear like a cotton shirt when it's cold outside and you get like kind of sweaty, it makes you even colder because of the fact that that water sticks close to you.
Cotton's good.
Sometimes cotton's good just because it's more like, yeah, it's more like light, okay? Megan, I think it has more something to do with how it's made, although I don't know for sure. I don't want to give you a wrong answer on that, okay? But if you have like Under Armour and then you put a sweatshirt on over it, now you're getting that layering effect along with whatever the Under Armour's doing, okay?
Are they really wooden?
Like an old pan, like, you know, yeah, sometimes they have a wood handle on it.
Or like when
It might be more like, it's like a wooden spoon. I mean, you know, same idea, but. Is that good there? Okay. If we go back to a term that we talked about on Tuesday, what would we say about the specific heat of insulators? What would we want them to be? We would want specific heat of insulators to be high. Okay? Because, Miriam, like we talked about before, things with a high specific heat don't do what very easily? Change temperature, right? So you want something that's going to maintain its temperature. Either a cool temperature if you don't want it to get hot, or a hot temperature if you want it to stay hot. So it won't change temperature. Because remember we said that temperature depends on the movement of particles, right? That's what temperature is. It's the speed of particles. If there's no particles, there's no temperature. Does that make sense? All right. Other hand. Okay, everybody, back up to Roman numeral number 3 now. Okay. Yes, I'm sure this time. Well, as sure as I can be. So a thermal conductor, by definition, material that conducts thermal energy well. That's where the well part comes. I'm sure you could probably name some thermal conductors, right? The metal part of the pan, right? Because Miriam, in that part, right, the actual cooking part, is the stuff in the pot actually in contact with the heat source? No, right? So we got to get that energy through the pot and into whatever it is we're trying to cook, right? So we want that part to be a good conductor because we want the heat to pass through it. Yep, because those things change. We want conductors generally to change temperature easily, right? If we just talk about like a metal rod, right? If we want the heat to go from one end to the next, one end gets hot, then that heats up the next part, then the next part, then the next part. We want those different parts to change temperature quickly so they can pass the heat on to the next part. Just go ahead. That they're cold because they are good conductors. They feel cold because what do they do with the heat in your feet? It conducts that heat out of your feet. Okay, go ahead.
What are the heat values? How do you know if it's
Those are generally known values, so we can measure them. Kind of like you measured the specific heat value of the metal on Wednesday. That's how we do it, basically. You can measure it that way.
yeah, but so like is there like a number that it makes it at least like
Oh, no, not necessarily. I mean, it's a spectrum, but a lot of your conductors are going to be more like under 1. You know, water is like 4. It's like 4. All right, hey, freeze for a second, please. Door. 6th grade? No. All right, hey, freeze for a second, please. Okay, even though the bell's going to ring, stop. So, I was supposed to give you a quiz at the end of the period, right? We'll push the quiz back to Monday, right? Which means most likely the test is going to be moved to block day.
yeah.
Most likely. Yes.
I promise